All right, good afternoon, everyone. So my name is Deriu. I will present the paper Improving ML to Query Systems through Re-ranking of Semantic Hypothesis. This is work which is joined by Zurich University of Applied Sciences and the University of the Basque Country. So let's look first at the motivation, so what it is about. And we are in the realm of text to SQL. So you have a question, a natural language question, and you want to translate this question into SQL and then get the response. So in order to have like a more natural way of interacting with your database. What I'm going to present today could also be applied to more general generation tasks, but we did the study on this text to SQL approach. Now, currently, most of the systems that we use for this problem are these neural approaches that include beam search. And if you use beam search, of course, you always get a set of hypotheses. And it turns out that the correct hypothesis is not always on top. So if we look at this example here, we have the question, how many students, how many different addresses do the students currently live in? And the gold query would look like this. So you have select, count, distinct current addresses from students. However, the system returns as their top hypothesis one where the attribute is wrong. And it has a high confidence. So if you look at the beam search score, in the end, you get a confidence of 99%, which is a bit problematic. However, the second hypothesis, which has already a very low confidence, would be the correct one. So basically, if we put this in numbers, if we look at the beam size of 15, and we look at not only the top hypothesis, but if we were able, using some oracle, to determine which of these 15 hypotheses is the correct one, we would have like a huge improvement in scores. So basically, if we do exact result score, so matching the results of the gold query to the generated query, this is basically this accuracy here. You see that in all the cases, in all the different cases where we have that we tested with Spider and some with some other data set, we always get a huge improvement. So basically with Spider, we get about 9% improvement. And the other one, it's even more, it's around 20%. So basically, if you have an oracle that would tell you which one of your 15 hypotheses would be the correct one, you would get a huge improvement. This also means that your generative model is already quite capable of generating the correct result or the correct query. However, there is some issue with selecting the correct one from your beam. And that's what I meant at the beginning. You can apply this kind of thinking also to other problems that involve beam search. So also for automatic speech recognition, we noticed that if you would apply this kind of oracle-based approach, you would get huge improvements. Of course, in real world, we don't have any access to such an oracle. So in this work, we try to find another approach to see how we could sort of add more uncorrelated information. So basically, this is what we have. So the process is we have our natural language as our input. Then we use our ML to query system, which gives us K hypotheses. So basically K SQL queries. Then we use a query to natural language system. So basically a back translation system, which we have built, in our case, a rule-based system that handles that. And then we have K different natural language back translations. So for each of the hypotheses, we create a back translation in natural language. So the reason why we use the rule-based system is that neural approaches, they introduce errors, which sort of mess up the whole process a bit. So even using GPT-3 doesn't work perfectly here. So that's why we stuck to a rule-based system. And then basically what we do for each of these back translation, we compare it using textual, semantic textual similarity to the original input. So we basically what we are checking is the query that has been generated and then back translated, is the back translation on the semantic level the same as the input? So this gives us a sort of a semantic score, which helps us to get more insights. Because essentially we hope that if the query is wrong, then the back translation will reflect the error. So basically using a wrong attribute name or whatever. And then the textual semantic similarity will notice that. And hopefully the semantic similarity between the correct query, if it is in the beam search, if it is one of the K hypotheses, will of course, or hopefully get better scores according to the semantic similarity than with the confidence scores, or the wrong ones. So basically what we have then is we have two scores. We have the confidence score from the beam search and the semantic similarity scores, and then we can apply different weighting schemes to combine these two scores. So basically one way would be just to multiply them. Another way is to use calibrated weighting. So basically the problem is that these two have different distributions, and using you know, some scaling.
So, yeah.
Yeah. Can you still hear me?
Yes, we hear you.
Yeah. Okay. So basically,
No, we can hear again. Yeah, that's good.
oh, is it better now? Sorry.
It is better. Maybe my system was with problems.
Okay.
That's okay.
Okay, good. So basically, what you can do in order to have a more, to put them in these two scores into the same distribution, is you can use some scaling approaches, sort of training a logistic regression on a held out set in order to put them into the same into the same distribution. And also we could also learn a learned weighting. So basically training a logistic regression on these two scores, which then returns a weighting. Another thing that we saw is that if the confidence score is quite high, then it's most probably already quite good. So we say that if the confidence score is above a certain threshold, we ignore the semantic similarity score. So we tried a couple of different weighting schemes. And if we look at the results, so we have trained it on 4 different systems with 2 different data sets. We see that if we just use the confidence score alone, then we get, like, you know, for instance, the spider with the bridge system, we get 71 points. Unfortunately, in most cases, using only the semantic similarity score, you would get lower scores, except for this system here. But using this weighting scheme, so combining the 2 scores in almost all the cases gives you higher scores than just using the confidence or the semantic score alone. And for each of the systems, there is a different weighting schemes that works best, which is a bit unfortunate, which means that you have to test which one is the best one. But that's okay, I think. However, we see here, for instance, for the spider value net, we get 3 points improvement. Also here, we get 2.5 points improvement. And for this data set here, the improvements are a bit bigger, up to 9%, depending on the weighting scheme. And here we compare it to the oracle. So we have still a big gap to the oracle. So the oracle meaning that if you would select the correct hypothesis from your beam, you still have a huge gap to that. Here, 10 points, 10 points. You're also still 10 points of gap. So there's a lot of room for improvement. But at least we got some, we did some steps on the way there. This oracle semantic, which we call this, basically, if we rank the hypotheses according to the confidence score and rank them according to the semantic score, if we had an oracle that would tell us which ranking to pick, then we already would also get a huge improvement already. But again, we don't have access to such an oracle, so we only know what would be the best case scenario. If we look a bit closer at the analysis, so what you see here is a bit of a distribution from semantic score and the confidence score here on the x-axis. And here in blue are the correct hypotheses and in red are the incorrect hypotheses. You see that those where the confidence is already very high, these are mostly correct ones, regardless of how good the semantics or how high the semantic score is. But you see, there are many cases where the confidence is very low. However, the semantic similarity score is quite high. So that means in those cases where we have low confidence, we can take the semantic similarity score into account. And one good thing is that if both scores are low, then the hypotheses are incorrect. So at least we don't get too many errors from that. So let's look at a couple of examples. So here we have one where where it sort of forgot to add a join. And we see, for instance, that confidence scores, they are the same for the two hypotheses. However, if we look at the semantic similarity score, then the correct hypothesis has a higher score. So this is one example where we have to sort of ignore the confidence score or disregard it a bit and put more emphasis on the semantic similarity score. And then if we look at a few other examples, just looking at the back translation, we see that if we have the input query, what's the average track size of tracks purchased from this address here? And if we look at the back translation, we see that the first one, according to the confidence score, is completely wrong. However, the semantic similarity score also doesn't give it a high score. But the second one, which is the correct one, has a higher semantic similarity score, although it has the same confidence. So this is again an example where the semantic similarity helps us to find the correct hypotheses. And here we have two other examples where this is the case. So basically here it picks the wrong attribute. So it should be the country Mexico, but not the status Mexico. And this one is also wrong because here the name is so the Mexico is referring to the name of the company, which is also wrong. So this is one of the cases again where the semantic similarity score has its highest score with the correct hypothesis. So yeah, this is basically our work, and I think this kind of idea can also be applied more broadly to any problem where you have multiple similarities. You might also sort of as future work think about using it as some sort of meta classification or meta selection kind of approach, because you could use the outputs of different systems as your hypotheses and then use this kind of re-ranking to find the best hypothesis. So there are maybe more uses than just what we have presented here. All right, I think that's it. Thank you very much for your attention.